we are going to discuss today the second episode of ethers and epoxide. In the first episode, we had discussed the structure of ethers and we had also discussed the preparation of ethers. Ethers actually are alkyl derivatives of alcohols and they can also be said as alkoxy derivatives of alkanes, and that is why they are being named as alkoxy alkanes according to IUPAC nomenclature. The outline of today's episode comprise of physical properties of ethers, in which we are going to discuss comparison of polarity of alcohols and ethers, or actually we will compare the boiling points and water solubility of alkanes, ethers and alcohols. We will then discuss the chemical properties of ethers, in which we are going to discuss reactions due to ethereal oxygen. We will discuss the reaction due to cleavage of carbon oxygen bond in ethers, and then we will discuss the reaction which involves alkyl group of ether like substitution reaction, dehydration reaction, etc. So, first of all, the physical properties of ethers. Ethers basically are weak Lewis acid. Now, what actually are Lewis acid? The compounds which have a lone pair of electron which they can give to other electron deficient moieties during the reaction. The availability of this lone pair of electron in ether is because of the presence of oxygen. The oxygen in ethers is sp3 hybridized and the structure of ether is a tetrahedral structure. Ethers exhibit dipole-dipole interaction. This again is due to two polar bonds present due to carbon and oxygen in the molecule. Ethers have a small dipole moment and they are relatively non-polar. They are actually inert to a wide range of reaction conditions which we will discuss later. A very good property related to ether is that they are very good solvents for a number of reactions. We will now compare the polarity of ethers with that of alcohols. The reason for this comparison is that ethers are the alkyl derivatives of alcohols. Now, if we compare the structure of the two molecules, you will see that here in this structure of alcohol, we have a possibility of hydrogen bond. This is possible because in case of alcohol, we have oxygen hydrogen bond. In case of ethers, this hydrogen is actually replaced by an alkyl group. There is no possibility of hydrogen bond in ethers, and as a result ethers have comparatively very low polarity than the alcohols. We will now discuss a few more physical properties of ethers. Lower ethers like dimethyl ether and ethyl methyl ethers are gases. Lower ethers are highly volatile and inflammable also, and they have lower density as compared to water. They show increase in boiling point with the increase in molecular masses. Now, in this table you will see that we have ethers here, this methoxymethane, methoxyethane, ethoxyethane, propoxy, propane, etc. And in all these cases you will see that there is a continuous increase in the molecular mass of these ethers, and as there is increase in molecular mass, there is a consistent increase in their boiling point. So, they show a pattern that with the increase of molecular mass, there is an increase in boiling point of ethers. Now, we will compare the boiling point and water solubility of ethers with that of alkanes and alcohols. Here we have diethyl ether, we have pentane and we have 1-butanol. The molecular mass of all the three molecules is almost similar, but if we look at the boiling point of the three, we see that ether has a boiling point of only 35 degrees, that of alkane, that is pentane, is 36 degrees, whereas alcohol has a much higher boiling point. Now, the question arises why? Why alcohol has such a high boiling point even though it has almost equal molecular mass compared to pentane and diethyl ether? And I think you all know that the answer lies in that the alcohols can have hydrogen bonding, which is not possible in case of alkanes as well as ethers. Now, look at the solubility of these 3 molecules in water. The solubility of ether and solubility of butanol, you can see that they are sufficiently soluble in water. Now, why ethers are soluble in water even though they cannot have hydrogen bonding? The reason is they have oxygen which can form hydrogen bond with water. So, it has solubility in water, whereas alkane does not have any polar molecule, polar atom in it. As a result, it cannot form any kind of hydrogen bond, and that is why it is insoluble in water. Well, on the basis of the structure of alcohols and ethers, we can draw certain inferences, like alcohols and ethers having less than 5 carbons are soluble in water because they can form hydrogen bond with water. Alcohols and ethers having more than 5 carbon atoms are insoluble in water. The reason is the non-polar alkyl group is too large to dissolve in water. Alcohols and ethers of any size are soluble in organic solvents like benzene, carbon tetrachloride, etc. We will now discuss the chemical properties of ethers. Actually, we have mentioned it earlier also that ethers are quite stable. The reason is ethers are alkane like molecules, and you will see that ethers do not react with bases, ethers do not react with oxidizing agent, they do not react with reducing agent, and even they do not react with active metals also. The reason is that they do not have any active hydrogen in them. The chemical properties of ethers actually can be divided into 3 main categories. The first is the reaction due to ethereal oxygen. The reaction here are possible because oxygen has pairs of electron which can be donated during the reaction. The second category of ether reaction involves the breaking of carbon oxygen bond present in ether linkage. The third category of chemical reactions shown by ethers are because of the alkyl groups, and the reaction normally shown by alkyl groups are substitution reaction or dehydration reaction. So, now first of all we will discuss the reaction where ethereal oxygen is involved. Ethers dissolve in strong mineral acids due to the formation of oxonium salt. The lone pair of electron on oxygen is donated to hydrogen ion of the acid to form these salts. Now, you can see here that this is acid and this is the lone pair of electron on oxygen. The H plus ion from the acid is donated to this ether, there is formation of oxonium salt here. Because of this reason, ethers dissolve in strong mineral acids and form corresponding oxonium salts. Like for example, here you can see that ether is reacting with sulfuric acid, formation of oxonium salt, and in this case ether is, this is methoxyethane reacting with hydrochloric acid, another acid, and forms oxonium chloride. The reaction of at the ethereal oxygen actually is possible at room temperature or at low temperature, and if the ethereal these oxonium salts are treated with water, we can get back ether easily. The reactions now where ether behave as a Lewis base, and this is possible because ether has oxygen containing 2 lone pairs of electron. Now, what happens here is that ether forms coordination complexes popularly known as etherates when treated with Lewis acid like boron trifluoride or aluminium trichloride. Here it is the formation of boron trifluoride diethyl etherate, the complex formed because of the reaction between diethyl ether and boron trifluoride. In the second reaction, you can see that this is methoxymethane or dimethyl ether reacting with aluminium chloride and generating aluminium chloride dimethyl etherate. Ethers are used as solvents in the preparation of organometallic compounds like Grignard reagent. Here again the basic property of ethers is used because oxygen here has lone pair of electron which are donated to electron deficient magnesium in alkyl magnesium halide, and there is formation of an etherate. Another reaction shown by ether is when they are exposed to air in presence of light for a very long time, they undergo spontaneous auto-oxidation and form hydroperoxide. This hydroperoxide then is converted into an explosive polymer called ether peroxide. Here diethyl ether is reacting with oxygen and forms hydroperoxide. This reaction is possible when ether is exposed to sunlight for a long time in presence of air. This hydroperoxide is converted into this ether peroxide which decomposes violently at high temperature. To destroy the peroxide from ether, ferrous salts are added. You can see here that into the ether ferrous ammonium sulphate is added, along with that potassium thiocyanate. Then there is formation of a red colored complex which indicates the presence of peroxide in ether. Now, how is this reaction actually taking place? Ferrous ammonium sulphate is iron 2 ions, that is ferrous ions. The peroxide oxidizes Fe2 plus into Fe3 plus, and there is formation of ferrithiocyanate which is red in color, and that indicates the presence of peroxide. So, if in a solution we have peroxide, in a solution of ether we have peroxide, if we add this ferrous ammonium sulphate and potassium thiocyanate and there is generation of red color, this clearly indicates that peroxide has been formed, and during the process, during the addition of ferrous ammonium sulphate, the excess peroxide is also destroyed from the ether. We will discuss here the distinction between ethers and alkanes, a reaction which is given by ethers only and not by alkanes. We have already discussed the reaction of ethers with acids, they form oxonium salt. You can see here ether is forming oxonium salt, whereas alkanes do not undergo this kind of reaction. So, if we have a mixture or if we have two substances, one is ether and other is alkane, we can very easily identify which of them is ether by undergoing reaction with acid. We will now discuss the second category of reaction shown by ethers, where there is cleavage of carbon oxygen bond in ether. This cleavage of carbon oxygen bond results into hydrolysis to form alcohol. We can see here that this is an alcohol reacting with water and there is formation of alcohol. You can see here, since this is an unsymmetrical ether, there is formation of two set of alcohols, ROH and R-OH. The nature of alkyl group is different in these two cases. Here it is methoxyethane. When treated with water and heated, there is formation of methanol and ethanol, two alcohols. The third reaction here is ethoxyethane reacting with water. Since this is a symmetrical ether, you can see that there is formation of only one alcohol. When ethers react with sulfuric acid, there is formation of alcohol and alkyl hydrogen sulfate. When they react with phosphorus pentachloride, they form alkyl halide and phosphorus oxychloride. The number of alkyl halide depend on the nature of ether. If we are starting with an unsymmetrical ether, there will be formation of two different alkyl halides. But if we are starting with a symmetrical ether like this one, here it is ethoxyethane, when treated forms ethyl chloride only. Now, we will discuss the reaction of ethers with hydrogen halide. Ethers react with hydrogen bromide to form alcohol and alkyl bromide, react with hydrogen iodide to give alcohol and alkyl iodide. When ethers are treated with hot halogen acid, only haloalkanes are formed. What actually happens here is that first there is formation of alcohol and alkyl halide, and then alcohol again reacts with another molecule of alkyl halide and form this alkyl halide. The order of reactivity of the 3 alkyl halide follows this order, that is alkyl iodide undergo this reaction fastest, then alkyl bromide, and then it is alkyl chloride. The cleavage of carbon oxygen bond by halogen acid follows nucleophilic substitution reaction. In case of cleavage of unsymmetrical ethers, there is formation of 2 haloalkanes, while in case of symmetrical ethers only one haloalkane is formed. Here we have taken the example of a symmetrical ether, so there is formation of only one alkyl halide. This is an example of unsymmetrical ether, so you can see here that 2 alkyl halides are formed. Similarly, this is also methoxy tertiary butane, and this reacts with hydrogen iodide and forms this tertiary butyl iodide and methyl iodide, 2 different alkyl halides. A symmetrical ether like ethoxyethane is forming only one alkyl halide. When halogen acid are reacted upon with unsymmetrical ether, it has been seen that the alkyl group, which is smaller in size, gets attached to the halogen side chain. This we can discuss it with the help of this example. Here we have an ether, one side of which is attached to ethyl group and the other side attached to the isopropyl group. Now, when HI react with it, there is a possibility then iodide can attach to this part of alkyl or this part of alkyl, but actually it has been found that iodide attaches to the alkyl group which is smaller in size, and this is due to less hindrance possible at this carbon. We have here an example in which a ethoxy group is attached to cyclopentanol. The molecule is called ethoxycyclopentane. When hydrobromic acid is treated upon with this ether, there is formation of cyclopentyl bromide and ethyl bromide. Out of the 2 alkyl groups, the availability or you can say less hindered position is at this alkyl group, and that is why halogen attaches itself to this carbon, less hindered carbon. Here again you can see this in this example we have ethyl phenyl ether. One side of ethereal oxygen we have a phenyl group and on the other side we have the ethyl group. You know that the hybridization of this carbon is sp2 hybridized, whereas this carbon is sp3 hybridized. So, here actually the attack of bromine takes place and there is formation of ethyl bromide. We now have a very interesting example. Here this is phenoxybenzene. This phenoxybenzene is an ether. At the same time, this oxygen is attached to 2 sp2 hybridized carbon. As a result, this carbon oxygen bond has a double bond character because of delocalization of pi electrons of because of the delocalization of the lone pair of electron on oxygen with the pi electron cloud of benzene ring. As a result, when this molecule reacts with hydrogen bromide or hydrogen iodide, first step, that is protonation, takes place, but in the second step when the nucleophile, that is bromide or iodide, has to attack the carbon, this bond does not break. As a result, there is no reaction with this kind of ethers. Now, we will discuss the reaction of ethers with hydrogen bromide which involves 3 steps. In the first step, there is protonation at the ethereal oxygen. This ethereal oxygen has lone pairs of electron which it can easily donate to electron deficient hydrogen here, and there is formation of this protonated ether. In the second step, the bromide ion which is generated in first step attacks the less hindered carbon of the oxonium salt of ether and generates alcohol along with an alkyl halide. In the third step, this alcohol which is generated in the second step again is attacked by the hydrogen bromide. There is formation of this protonated alcohol, removal of water molecule and attachment of the bromide, or you can say nucleophilic substitution by the nucleophile as a result there is generation of another alkyl halide. So, overall all the three steps for the formation of alkyl halide from ether comprise of reaction of ether by two molecules of hydrogen halides. We will now discuss a case of ether where one of the alkyl group is tertiary in nature. For example, you can see that this is a tertiary butyl group and this is a propyl group over here. Now, when there is a tertiary butyl group, then the reaction, this substitution as well as elimination takes place because the reaction follows SN1 mechanism. A tertiary carbocation is formed during the reaction which can undergo elimination to form alkene as well as substitution reaction to form alcohol. You must be knowing about this SN1 type of mechanism in which first there is formation of carbocation and then carbocation undergoes either substitution or elimination to form the substitution product or elimination product. Here you can see that there is formation of this tertiary butyl carbocation which can form this tertiary butyl bromide because of substitution reaction. This can form isobutene because of elimination. Now, we will discuss the reaction of ethers with acetyl chloride and acetic anhydride. In both the cases, we get ester formation and the reaction takes place in presence of anhydrous zinc chloride or aluminum chloride. Here you can see that this is ethoxyethane. It reacts with acetyl chloride in presence of zinc chloride to form this chloroethane and this ethyl ethanoate. When this ether reacts with acetic anhydride under similar conditions, it forms only esters. We will now discuss the reactions of ether where alkyl group of ethers are involved. The reaction shown by ether due to the alkyl groups are dehydration reaction, and dehydration results when ethers are passed over heated alumina to form alkenes. Here you can see this is diethyl ether passed over heated alumina, that is aluminum trioxide in at about 300 degrees centigrade, and there is generation of ethene. Next reaction of ether where it reacts with carbon monoxide at high temperature and high pressure conditions, and again there is formation of esters. We will now discuss the halogenation reaction which takes place in ethers. Ethers actually are alkane likes, and that is why the alkyl group of ether are halogenated when treated with chlorine or bromine in absence of sunlight. The substitution takes place at alpha carbons of the ether. Here you can see that in this case, in this ether, the alpha carbons are this carbon and this carbon, that is the carbon attached to oxygen is called alpha carbon. Now, these two the hydrogen attached to these alpha carbons gets substituted by chlorine. Here you can see there is formation of 1-chloro diethyl ether because only one of the carbon is substituted by chlorine, whereas in this case both the alpha hydrogen have been replaced by chlorine and the resultant molecule formed is 1,1-dichloro diethyl ether. Now, if diethyl ether is treated with chlorine in sunlight, then all the 10 hydrogens gets substituted by chlorine and we get per-chloro diethyl ether formation in this case. We will now discuss the mechanism of halogenation. If you remember the mechanism of halogenation, the first step in the halogenation step is the formation of a free radical. In presence of sunlight, the covalent bond between chlorine breaks homolytically and there is formation of this chlorine free radical. Now, this chlorine free radical abstracts alpha hydrogen, either this or this, from ether, and there is formation of another free radical which is stabilized by resonance, and then this free radical is treated with another molecule of chlorine, there is formation of 1-chloro-diethyl ether. Now, this reaction does not stop here, because this is a chain reaction, and once this hydrogen is substituted with this chlorine atom, another hydrogen from this alpha hydrogen also goes off, and if we undergo the reaction in sunlight, there is such a huge amount of energy available for the reaction to occur, that all the carbon hydrogen bond gets homolytically broken and they are substituted by chlorine. As a result, there is formation of perchlorodiethyl ether. So, with this we have discussed the properties of ethers, and we will once again summarize what we have discussed in today's episode. We have discussed the comparison of polarity of ethers with that of alcohol. We have compared the boiling point and water solubility of ether with that of alkane and alcohols. We have also discussed the chemical properties of ethers, in which we have discussed the reactions shown by ether due to ethereal oxygen. We have discussed in detail the reaction where cleavage of carbon oxygen bond takes place in ether, and we have discussed the reactions involving alkyl group present in ethers, and the reactions normally given by alkyl groups are substitution reaction and dehydration reaction. In the next episode of ethers and epoxide, we will discuss about epoxides. What actually are epoxides, their